And I'll also be presenting some slides. So probably we can, if you can give me screen share rights,
Sure. The
I
screen
will.
share right will be given.
Okay.
Hi, Jay. You're there?
Yes, I'm there.
Okay. Dr. Bhatt, Jay would be introducing you to the to our delegates, and from there we'll start your session. And the Q&A, as we have informed you before, it would be a moderated question answers. So Jay will be moderating, or rather curating the questions for you, and from there we'll lead forward.
Okay. So
Yes, good afternoon, everyone. So we have Dr. Rushi Bhatt with us. He has pursued his PhD in cognitive and neural system from Boston University. Currently, he is a head of artificial intelligence at LinkedIn, Bangalore. Prior to LinkedIn, he worked in Amazon as a machine learning scientist and a manager. He also worked as a research manager in the Yahoo Labs. Without a further ado, I will request Dr. Rushi Bhatt to start with.
okay. So I will. Are you able to see my screen?
Yes, sir.
Okay. All right. So let me just go into presentation mode, and then I will. Okay. You can see the screen, right?
Yes.
All right. So I'll give you a brief overview about applied machine learning and how we use machine learning for a variety of applications at LinkedIn. To give you a little bit more in-depth experience of how applied machine learning gets carried out at scale for business critical applications, I will take you through a couple of examples through multimedia machine learning that we apply here at LinkedIn for the entire LinkedIn feed. So to give you a very high level overview of what is a machine learning use case lifecycle in a real applied setting, right? So if you can look at the the bottom left, ideally what to give satisfying experiences to the user, right? So the user provides us with behavioral signals, and based on the signals, we want to give the best user experience. So in this case, for example, you want to show like very high quality jobs recommendations, and what comes in from the user is they express their needs in terms of finding the right jobs. When we show them the right jobs, they apply to the job, and sometimes they are successful and they get the job, and we get the signal back saying yes, that user has taken up the job. So the product metrics in this case for the company will be something like how many times did the user click and apply for a job, how many times post-click through tracking we find out that the user has actually changed the job, or we find that somebody from the job suppliers recruiting team got in touch with the user and the conversation went forward and so on, right? Now, those are not the metrics that we can directly optimize on, because user success is number one, a lagging feature. Number two, as you can imagine on LinkedIn, if you have a LinkedIn account already, how many times immediately post taking up a job you update the job page, right? And the third thing is the attribution. So sometimes you would apply for a job on LinkedIn, but at the same time somebody else got in touch with you, or you got a job through a friend's referral. So it is not entirely accurate to say that every job that has been taken up by through LinkedIn only, right? So the attribution also becomes a very difficult question to answer. So from machine learning building, we cannot directly optimize on the product facing metrics like the number of applies and the number of times you joined a company and so on. So what you would do is you would create relevance metrics like the internal facing machine learning metrics that you can directly try and maximize, right? So one relevance metric could be how many times when a user was shown a job, did they apply for a job, right? How many times did somebody interact with a job? So when you were shown a job, you clicked on the job and maybe went to the company page, or you looked at the internal the whole job description and spent some time looking at the job description and so on, right? So those are the relevance metrics that you can directly optimize on, rather than just the product facing metrics, right? And then once you have a good understanding of what your relevance metric is, you can apply machine learning. So you have a variety of optimization frameworks, you have a variety of machine learning algorithms, and the input features like your job profile, your seniority, what is your current title, which company you are working on currently, and what is the job feature, like what are the skills required for the job, and what is the seniority of the job, and so on. Both sets of features together can be given to a machine learning algorithm that optimizes the number of applies and so on, right? And then the most important critical part in any machine learning application is how do you evaluate the performance of your classifier, right? So I can come and tell you, oh, my classifier is the best in the whole world, right? But what we have to do is you would have to do an A/B test, right? So you have a baseline method. Maybe that is either a well accepted method in the industry, or it is something that is already running in production, right? And your new algorithm is compared against that method to see how well it is doing in terms of user performance metrics. And here again, you would come back to the product metrics, right? And say, okay, what are my product related metrics, and how well is the algorithm doing in optimizing those product facing metrics, right? And generally what you would do is you would randomly partition your user set. You can say, okay, I'll randomly select 5% of my users, show them the new algorithm B, right? 95% of the population remains with algorithm A, right? And I will compare what is the lift, if any, in the algorithm performance. And if the lift is positive and statistically significant, then I will go ahead and roll out the algorithm to the entire population. So there also, again, there's a lot of statistics that go in hypothesis testing and so on, right? So now this is good. I mean, this is a good foundation basics, right? But what are the real challenges in applying machine learning at scale, right? So number one, too many algorithms, right? Now you can imagine every day somebody is publishing a new algorithm. You want to try it out because we don't know which algorithm will work for a specific application. So you need to have that flexibility to apply different algorithms. There are also too many technologies. So TensorFlow is one way of implementing algorithms. PyTorch is another. There'll be some legacy libraries that a company will also have, and that also needs to be utilized, right? And also, like I said, every day a new algorithm comes in. State of the art is advancing quickly. And there might be also situations where the best models that are working offline in your experimentation will not be servable because the cost to serve is very high. You need so many servers, and each server has a cost to rent on the cloud, or you have to buy a server and so on, right? And when there is so much variety in the technology, algorithms, and so on, there is a lot of friction in the build, launch, observe cycle, right? So you would build a classifier, launching requires a lot of development work, and then you have to observe the output of the classifier for some time, and then maybe also iterate and all, right? So if your build and launch pipeline is not very well tuned, then you spend a lot of development time just trying to experiment, and each experiment becomes very expensive, which means you cannot do too many experiments, right? So those are the issues. And then in real world, then you have to also worry about the platform and tooling that can support the kind of experimentation that you want to do with the variety of classifiers that you have at hand. So what we have done at LinkedIn, and the next slide will show you much more detail on that, is we have really created a standardized layout of machine learning pipelines that allows for exploration. It allows for seamless touch-free or push-button deployment of models. And it also integrates very well with offline and online systems. Now, offline and online systems is another thing that you have to be really careful about when you're working in practice, because sometimes the variables that you observe online and all the inputs that your classifier has available online while serving traffic, if you're not doing a good job at tracking that content or all that information, then you will not have access to those variables offline, or you will have scale information offline, or it will be in incorrect format, right? In text classification, for example, it may very well happen that you have some tokenization and pre-processing happening during your online classification, but you're not applying the same method offline, and therefore your tokenization is a little bit different when you're building classifiers versus when you're serving traffic, and that itself can lead to performance loss, right? So you really have to make sure that there is offline online parity and so on. So these are core engineering questions that one has to solve while you're worrying about how to deploy machine learning in practice online, right? Another, as I mentioned earlier, also robust A/B testing and performance analytics. You want to be able to audit and reproduce your experiments. You want to do further analysis, like whether your classifier is working better in some segment. Let's say, for example, it's working well in India, but not in Japan, and so on, right? And you want to automate as much as possible so that there is less reliance on humans, and therefore less mistakes made by the human operator, right? So things become more predictable that way. And more and more with GDPR, with CCPA, which is the California law for transparency, and also India is coming up with new laws about transparency and data security. You also have to make sure that your algorithms are compliant, right? So you're not using data that the user has not consented for using. You're using only the data that in its current form, in its right format, and you're not leaking that information to the external world while deploying your classifiers and so on, right? So the compliance and data security is really part and parcel of the platform and machine learning tooling that you have to build. So with that, I will give you a very brief introduction of our internal system. We call it ProML. So this is not professional ML, this is productive ML, right? We want to make sure that our machine learning system is as productive from the point of view of cost to serve as well as the developer time. And therefore, we have this initiative inside LinkedIn. It's called ProML, right? And there is a platform associated with it. And it has multiple layers of development and deployment, right? So this ProML platform really tries to solve all the challenges that I showed you in the previous two slides. So number one, of course, we want to make sure that the exploration, like coming up with new models, trying out different features, trying out different new algorithms, that becomes as easy as possible for your developers, right? So your machine learning engineers or your data scientists. So for that, we have an authoring layer, and I'll show you a little more detail in the next slide as well. What we have done is we have a domain-specific language, DSL, and we have a Jupyter Notebook interface to that DSL. So you can write very declarative kind of model specifications using a customized language that the systems understand throughout the stack, right? So the serving system understands the script, as well as the development system understands the script through Jupyter Notebook, right? And then we have connections to several training machine learning libraries. So there is an open source version of LinkedIn called PhotonML. So that is for large scale mixed effects, random effects models. Then there is XGBoost, of course, which is very popular in certain areas of machine learning. And of course, TensorFlow for deep learning and certain other kinds of classifiers. So what happens is when you're done with your exploration and feature exploration or data analysis through your Jupyter Notebook, you have authored your model file in the domain-specific language that I mentioned, then that domain-specific language also can be plugged into all these training libraries to create a model, right? So for example, you could create a TensorFlow graph and then throw data at it on the Hadoop clusters or on Spark clusters, and you will get a TensorFlow protobuf that can be directly deployed into the serving systems, right? So that brings us to the deployment. So the moment your model artifact is ready, all your coefficients are ready, then you can take those coefficients and put into the serving systems. And we have ensured that all the features that were available offline during training will also be available online during serving. And that is the online-offline parity that we have achieved through a separate layer of LinkedIn APIs, which is really an abstraction layer for the data. So what you can think of, so if you're familiar with Java, Java has a concept of namespaces, right? So each class will have like com, LinkedIn, feature importance, right? And that class knows how to do feature importance. The same way, we have created a namespace even for features. So you could have something like com, LinkedIn, member age, and member age is available during training offline as well as during runtime when the model is deployed in production. And that is an entire software stack that we have to build to ensure that the developer doesn't really have to worry about where the data comes from and how to deposit the data into the serving. It is just available to them as soon as they instantiate the model feature space, the feature namespace class into their code, right? And then, of course, there is A/B testing and monitoring that we just mentioned, and all the data automatically flows through auto sensing into the tracking data and dashboard. So this is really the ProML platform stack, which takes the developer all the way from initial exploration and data analysis to final A/B test and monitoring. And many of these things are just part of the tooling. You can go to a dashboard and launch your model and look at its behavior in an A/B test right from your desktop. You don't really have to worry about doing multiple manual um, um, steps to deploy and look at the behavior of your model, right? So I will, in the interest of time, I'll go very quickly through this slide. But this is like the zoomed in version of the part I was telling you about, where you have a feature marketplace where all the feature with their correct namespace is available that a user can, a developer can use offline to do their experimentation and all that. And once the model is ready, on the top right, you see something called model registry. So once you are satisfied with the model, the offline performance of your model, you would go and register your model into the model registry, and the serving systems will pick up from the model registry. So you can think of it as a database entry that says, hey, this is a model for jobs recommendation. This is number 5 or version 5.3. It uses all these features and transitive closure of all the features. And the serving system understands what this model is and where to pick up the features and do the service through either a REST or through a Samza streaming protocol. And the entire model can be brought online just with a push button. Like I said, this is really a very quick glimpse into our internal domain-specific language for model exploration and authoring, right? So this is something you would probably write in a Jupyter notebook when you're developing a model, right? So you can see something like there is a new feature producer which takes in title embedding from some neural network. And so title is like, for me, a title will be like director of engineering. For someone else, it will be like a software engineer and so on, right? So you would take a job title and the embedding of a job title and an embedding of a user's title and try to do a cosine similarity, right? So that is the operation between lines 76 through 79, right? Another cosine similarity also happens. And then we would instantiate a decision tree model in line 86, that is a decision tree scorer. And it gives you back all the scores that can be ordered by score, and the list can be returned to the caller, right? So that happens in lines 88 through 90. But not to go too much into details, we are planning to open source this domain-specific language anyway, so you will see it soon. But the idea is to make machine learning development process as declarative as possible, so that you don't have to write a lot of boilerplate code. You can really just instantiate all these features just the way you would. And the training system as well as the production systems will have equivalence, and they'll both be able to create exactly the same features. So there is no disparity and confusion when you go from offline to online. So with that, I will switch gears a little bit, and we will go into some of the applications that you may find interesting. So I will focus more on the multimedia side, because that's where we have seen tremendous success with very large data and very large scale modeling that we have done at LinkedIn. So as you may all be aware already, deeply neural networks are seeing a resurgence in the last 10-ish years. And there have been several very challenging data sets. So one of them is ImageNet, of course, which is about 1,000 different classes and about 1 million training examples across 1,000 different classes that one has to classify a given image into. And you are now seeing that the human performance is systematically being beaten by machine learned classifiers. So all those things are great. You also have challenging data sets out in the open. There are some open source models that are also working very well, like the ResNet model and so on, right? Why would you create a separate technology for a specific company, right? So like LinkedIn, why would we invest in a different set of classifiers? Why not just use open sourced data and classifiers and just download them and run them, right? Now, what happens in LinkedIn's case is the distribution of the data is slightly different from what you will find in a randomly sampled data set, right? So we are a professional networking site. You will see more slides and web graphics and charts because that's professional content. You will see like conference pictures. Who knows, maybe we'll see some Zoom screen grabs from this presentation also on LinkedIn, right? And we want to understand that content either for personalization or content recommendation, or to make the content searchable and retrievable, or for if you're visually impaired, then captions of those images can be very useful to understand what the post is about, right? So what we find at LinkedIn is about 60% of all images contain some kind of text or the other, and about 70% of videos also contain some text in them. So it makes the classification and the content understanding problem is very different from what can be solved with just downloading open source models, right? So what we have found is when we pick up um, uh, existing classifiers and retune them through active learning plus transfer learning, it works a little bit better than using just the open source downloaded content for these purposes. So to give you a little bit of an overview of how the LinkedIn content differs. So if you look at the left-hand side data set, that is really the ImageNet data set, and the captions on the open image data set, right? So you'll see trees and wheels and windows and plants and cars, right? Clothing is the biggest phrase that comes up when we create captions for these images. Versus when you look at LinkedIn feed classes, you will see chair and light and glass, microphone, light bulbs, right? So the setting of these scenes tends to be very different from like a general natural image, and therefore we have to pay much more attention to these types of classes when we create these classifiers. So another example is here. So here are the kinds of images that we see usually on LinkedIn. So you will see like industrial images, work sites, some machinery. You will see professional conferences, and as I was saying before, also there's a lot of background text that we also need to parse in order to understand what the setup is to understand these images, right? So the images are diverse and also unique in many ways. So just to show you some example, and I'll take you through details of the solution as well. The modeling, when you take LinkedIn specific data and LinkedIn specific models and retrain the models and so on, you can very frequently beat state-of-the-art commercial solutions even. So for example, for OCR, we find that our F1 score is about 38% better than the best commercial solution available to buy, right? image captioning and all also show much better than average when we look at the commercial solutions. Now, this is not to say that the LinkedIn solution beats the commercial solutions across the board. Probably not, right? Because these classifiers are tuned to content that is very specific to the LinkedIn feed, right? So you would expect some boost here at probably at a cost of some deterioration in performance for images that we don't routinely see on the um, LinkedIn feed. So just to show you one more example of why these kinds of applications are important for LinkedIn, right? So one potential application is, like I said earlier, accessibility, right? So usually what happens when you go to LinkedIn feed, and if you're not visually impaired, then you will not really notice. But a lot of updates are really just an image, right? Or just an image with something very unspecific, like it was a pleasure, right? And then there'll be a person talking to an audience or something, right? Or it'll be an infographic like the bottom image in this slide and so on. So it is very important for accessibility as well as for content recommendation and retrieval, right? And also for content personalization, that we extract as much information as possible from the scene that is given. So, so you will also see that when you tune the classifiers to the application, it works much better. So one example is a commercial application API will give you, for the first image or the top image, it will give you only a room that has a sign on the screen, right? It doesn't really mean much, but a better caption, which the LinkedIn model produces, says a man standing in front of a projector screen, right? So that is much more informative. A picture of a logo, that's also more informative. The last one is actually much better. So instead of saying a screenshot of a video game, this is not really a video game anyway, right? It says a close-up of a graph. Now, it doesn't say this is a graph for some jobs changing behavior or something, but at least you know that there is some graph and some statistics being shown in the image. So the other example here, that is our internal favorite, is really capturing the intent and the semantic description. And this becomes a very difficult problem if you are just given one slide and you have to understand what is going on, right? So at least the LinkedIn model does a decent enough job. It says a man speaking to a group of people, right? We still don't know what they're talking about, right? A commercial API model will say a group of people sitting in front of a computer screen. That's even less accurate. The ideal caption, when we give these images to crowdsourcing workers and they come back with ideal captions, they would tell us that the ideal caption here is a person presenting on immunoaffinity to a group of people, right? And imagine now the complexity of the task here. So we not only have to understand the situation, like there is a professional talk going on that somebody is listening to, right? Because a man presenting slides, right? That's a professional talk. But we also have to understand what the talk is about, which is really some technical matter, which means we'll have to do some OCR on top of just the scene understanding to come to this. So we are not there yet. We are still at the first part where we are able to say a man speaking to a group of people. But the next challenge is, of course, to go deeper into extracting information, OCR, text, logos, etc., to understand the scene even better, right? So as you can imagine, this is a very difficult problem when the only thing that is given to you is really image pixels with no surrounding information. And this is also difficult because we are looking at very short form LinkedIn updates and posts rather than entire web pages. So on web pages, what happens is there is a lot of metadata that comes from the domain information, which is not available here, right? The domain is always linkedin.com. There's a lot of other text that surrounds an image that can also be used just in the NLP and text classification sense. That can also give you a lot of information. But here, all we'll have is it was a pleasure talking and an image, right? So the understanding problem is much harder than the general web page classification as well, right? So what we did here was we said, okay, all right, so we can't just boil the entire ocean and build everything from scratch. Why don't we take a commercial API application and try to understand whether the caption that is generated is good or bad, it is relevant to our application or not, right? So this is really a starting point. And remember, I'm trying to take you through the journey of a machine learning application development. I will not have time to go through all the nitty-gritties and all the steps that we took. But what we did was we trained first a meta classifier that tells us whether the API that is given, the caption that is given by an API is good or bad, right? And if it is not good, then we have to do something else. Now, what is that something else? We'll come to that in a bit, right? But this itself, where we could filter out or replace one potentially bad caption with another possibility, that itself gave us about 20%, 200% improvement in the coverage of the classifier. So the percent of times we could give a very good caption for an image, right? And it also boosted several other performances, right? So that was good, but remember the image I showed you, there is a lot of information in the background or in the scene that is not given just by vanilla captioning models, right? Because captioning models will do object recognition, and then they will probably use some type of attention-based or LSTM style caption generation mechanisms to get a description of, like a textual description of a scene. But a lot of information is left behind on the table in terms of all the text that also exists or the logos that exist, right? So then we said, okay, let's also try and extract all the text information from the scene, and together we will be able to get a better caption. Remember, our gold standard is to go back and say a man presenting in a professional setting or presenting to a group of people something about something, right? And that something needs to really come from the text that exists in the image. So that's one. And like I told you before, also 60% of images and 70% of videos contain some style of text or the other. So there may be a logo like the STM here, or there may be a banner in the background or some slides, right? Sometimes we also see some commercial promotional kind of content that we want to not show very frequently on the LinkedIn feed. And that also generally has much more text than average, right? So what we did, and this is a little more detail into how we can apply modular machine learning techniques and really change them together and get better performance just out of the box without having to reinvent the wheel every time, right? So what you would find is there are certain APIs that are already available, or you may even have built a text recognition model, right? That works really well on normalized images. But guess what? When something is projected on a surface, there'll be a skew and there'll be a little bit of a rotation that is projected to a 2D surface. So you will never see text perfectly aligned, perfectly parallel to each other, and so on, right? So there'll always be some skew that needs to be corrected. The text never is the only thing on an image. So you also have to detect where the text is and draw some bounding boxes and so on. So the approach we are taking is really chaining together multiple classifiers and multiple processing steps to get the final product, rather than bundling everything into a single model, which may or may not work, or even if it works, it will require far more data than attacking the problem piecewise, right? So we have really created an OCR pipeline at LinkedIn, which led to the performance improvements that I showed you earlier. So first you would do the text detection, draw the bounding boxes, find out where the text is in the image. Then you would do some region correction, rotate the images until they are really suitable for a text recognition model. And then finally comes the OCR model, and there you could build your own model or even download a model or use a commercial API, whatever is available to you, because that's probably the most heavy operation, followed by some post-processing, right? So sometimes what happens is, just based on the distribution of the text you are normally seeing, you can correct for OCR errors, right? So you could use a dictionary-based approach, or you could create your own vocabulary based on the kind of content that you're seeing in your application. You could even use a language model if you're trying to understand entire chunks of text rather than the little snippets that we generally see on the LinkedIn feed, and so on, right? So as you can see here, so by tweaking these individual components, pre and post processing accurately, and also using our own data to tweak these classifiers, you can see much better performance on the LinkedIn dataset, right? So so we are able to handily beat like about 20% improvement in precision and recall when we use custom pipelines on top of commercial APIs rather than using the commercial API out of the box, right? So in practice, sometimes either you don't have the time or the GPU power or the data to really build stuff from scratch. And many times building stuff from scratch is not even necessary. You can really just fine tune what is available to you and be a little bit creative, identify where the biggest performance issues lie, and try to really just correct for those performance issues and see whether your data distribution is different and where it is different, so that you can really just correct for the application that you have at hand. Now, like I was saying before, because you're doing really well in your own application doesn't really mean that you will generally do very well, and that is okay too, right? So it's not like LinkedIn solution is beating commercial applications everywhere, right? In fact, it is a close second to the best commercial API that we could find on the internet. And that is okay, because this is the application that we have to solve for. And this is remember the business metric that I showed you in the first slide. This is the business metric we have to optimize on. As long as you are meeting the business metric, you are doing a pretty good job. Some more examples of how the LinkedIn solution works on LinkedIn's data compared to some of the commercial applications. So here, for example, FORTS is an open sourced model. So it has an F1 score that was not the worst, but not terrible either. But hang on, sorry, I lost my message. Okay. Are you able to see my screen again? I think there was some flicker. Hello?
Your screen is visible.
Okay, awesome. Sorry, there was some interruption in my screen.
Yeah.
Yeah, so FOTS is an open source model. Now, like I was saying, it doesn't do really well. A commercial API also doesn't do super well, although it does better than the FOTS model. And the LinkedIn solution is actually better. Now, here is where, so in the previous one, commercial API was doing a pretty good job already. There was a lot of text that was not very skewed. It was all typewritten, so it worked out. But here, for example, there is an image in the background, right? There is some stuff on somebody's T-shirt. I don't know if you can see it, but the everyday part is really a logo on somebody's T-shirt, right? So FOTS did it, the commercial application did not. But on the other hand, FOTS could not really understand the logo in this person with the black T-shirts top left part, right? So, so the point here is different applications need to be tuned through in-house data, through some in-house pre and post processing and corrections, right? And then we can do a pretty good job at the final application as well. So here with LinkedIn solutions, you can really understand the company, its Poundland, and there is something amazing also written on people's badges and things like that, that can allow you to do a lot more than other stuff, right? And the other thing to be noticed is the Poundland part is really also, there is a dictionary part into the system. With dictionary lookups and brand lookups, we can also correct for a lot of mistakes like Poundland or Poundland, right? Those things, unless you have access to a brand dictionary, you can't really say what the real world should be, right? And this is pretty much the end of my presentation. But another application where we have seen a lot of success with the OCR solution is on catching promotional and viral content, right? So what happens is when we started doing promotional content detection, which is not something everybody comes to LinkedIn to view, right? It's a professional site. You want to see more professional news rather than advertisements. So it is important that we detect this kind of content. So when we started identifying promotional content, people were posting a lot of text. And then we got better at text spam classification and text promotional content classification. People realized that their posts are not getting enough distribution because LinkedIn is catching and curtailing all that content that should not be on the feed per our policy. So they moved to putting promotional content into videos and images, right? Thinking that it'll become more difficult. And spam catching is always a cat and mouse game. So now what we have is an OCR solution that extracts text from all these images, and we can feed that content now to the original text classifier that can now catch this content as well, right? So sometimes you also have to be inventive in how we respond and react to the changing customer behavior. Here, this is a negative customer behavior, but still something to be worried about. So in other words, there are all these other applications like OCR or scene understanding detection that are not just for the direct application, but these items, these classifiers are now feeding as feature items into other classifiers meant for different applications as well, right? So that's another thing to think about when you're building your machine learning application, where it is important not to hyper tune just for what you started with, but if you build things in a generic way, if you are able to publish your features in the sense of software engineering, where everything is accessible and consistent, then many other unforeseen uses can also come out of the feature and the classifiers that you're building. So with this, I'll end my presentation, and I'll be very happy to take any questions.
Yes, thank you, Dr. Rushi. We have a question from Monica. She asks that how viral content in videos be detected at a scale.
So viral content, see, so one part, the majority of my presentation here was on multimedia, right? So that provides you the signal on what kind of content it is. Like you can use those signals to classify the content. Now, the other thing is we don't necessarily want to always stop all virality. You know, some of the virality is also good, like a very interesting news item comes out, then you don't want to stop it either, right? So it is not like every time something goes viral, we need to stop it, right? But we need to detect whether something is going viral or not. And if it is going viral and if we think stuff is potentially bad, then we want to do something about it. Now, going to the question of how to detect virality, right? So there are machine learned ways. You can look at a lot of time series forecasting. So some of the most interesting features you will find will be related to the momentum. You know, so the rates, like how many likes, shares, comments is a piece of content getting. That's by far the most important feature in detecting and predicting virality. And of course, by predicting virality, I mean catching the content before it goes super viral and it has done any damage that it might have. Or if it is really going viral, then sometimes editorially also you want to give it a little bit more push. So momentum term is important, social graph and the reputation of the person posting, So I don't know, Narendra Modi posting something versus me posting something. The chances are Modi post will go much more viral because he just has better network reach. He has a more eager audience that is readily sharing and resharing what he posts and so on, right? So those are also graph related features and reputation related features. Those are also very important. And the third thing is, of course, you can also look at the correlation, like is the same content being reshared independently, right? Now, chances are if a lot of people are sharing the same content, the same news article, then the chances are that this content is interesting enough, and therefore it'll likely go viral. So what one can do is take all these features, right, and try to build a predictive model, right? So it can very easily be transformed into a classification problem where the binary question you're asking is, will this content be in the top K most viral content tomorrow? Or will this content cross the threshold of 1,000 likes in the next 24 hours? You can formulate the question in many ways. But once you have formulated your business question, then you can really build any classifier with all the features that I just mentioned. But yeah, I mean, several ways of building virality detectors. The most important thing is there is a time angle to this problem. It is very easy to say, oh my God, this thing went viral because it went viral and you found out that this is the top trending viral content, right? The more interesting business case is when you can identify content before it goes viral, right? So that either you can stop it if the content is bad, or you can boost it even if the content is good and it's going viral, so it is potentially interesting.
Okay. There is one more question which is asking that, okay, how LinkedIn handles deep fake images?
Right. So I think deep fake images, see, LinkedIn has many other signals beyond just the deep fake images question itself, right? So yes, you could build several classifiers. I mean, there are adversarial style classifiers that can also identify deep fakes. What is more interesting to LinkedIn is where the deepfake is actually utilized. So you would find that deepfakes are utilized more for creating fake profile pictures, which are also associated with fake profiles, right? Or it would be as part of a fake news item or something like that, right? So ideally, what you want to do is, yes, you could build a deepfake detector. It will have a limited um, precision and recall. But ideally, you want to see what is the other side information available. Like, is this person with potentially deepfake profile image also acting suspiciously? They are sending too many promotional content, or they are sending too many connection requests, or they are sending too many invitations, but nobody is actually connecting with them, and so on, right? Those kinds of side information can also provide you much more signals than just a deep fake classifier itself, right? So this really goes back to like trying to understand what is the business problem that you're trying to solve, rather than just trying to detect deep fakes for the sake of detecting them, right?
Okay. So I have a question which is related to the this deep fake, or you can say that, okay, many people, those who build their profiles and all. So how does LinkedIn work on the the reality of the profile? Does it perform some verification, validation of a particular thing which has been posted by a particular person, or about the profile? Is it like any sort of testing is done over there? Verification,
Right. So
validation, you can consider.
yeah, so fake profile detection is actually a very large project at LinkedIn. As you can imagine, it is also a very large project at Facebook, right? So both for Facebook as well as LinkedIn, the crux of our trust system is really real identity, right? So, for example, at Twitter, I believe you can create a handle that is not really your name, right? At LinkedIn and Facebook, that is a violation of our terms and services, right? So that's a very large team. My counterparts in the US run that team. And if anyone is interested in more details, I'll be more than happy to connect you with the right people. Just send me a message on LinkedIn and I will take it forward from there.
Okay. We have a question from Manoj Kumar, and he wants a solution, like what is the motivation behind picking up the ML projects, as most of the real ML projects are really an R&D class projects. How is ROI made on such projects?
Right. So that's not how we look at it at LinkedIn. In fact, everything that that LinkedIn does has some machine learning component or the other, right? So as the saying goes inside LinkedIn, machine learning AI is like oxygen at LinkedIn, right? There is no application where there is not a machine learned classifier deployed. Now, so it's well beyond the R&D realm, right? Now, and this is what you will see also in the presentation that I just gave you guys. We don't really go and build the next generation OCR model or the next generation, I don't know, speech synthesis. As much of the possible. R&D the data. And one of those things, virality, is actually an ongoing project in my own team. So where necessary, we do R&D, but generally the bias tends to be, how do we solve a user-facing problem? Now, when you ask that question of how do I solve a user-facing problem, the ROI becomes very self-evident, right? Because like I showed you very early in the presentation, you would build a solution, you would deploy it in production and see if it makes a difference on the business-facing metrics. So if you're showing, if you have deployed machine learned model, then instead of a rule-based model for advertising, you'll see a lift in revenue. If you put machine learning instead of a hardwired model for feed ranking, you will see an improvement in feed ranking, right? In feed engagement and so on. And if you don't see such lifts, then probably you need to work a little bit harder, right? But the LinkedIn product is assuming that AI comes first. So the question of whether to use machine learning, I think we are well past that. Now it is a question of where to invest the most. And there we go with user-facing A/B tests, and the ROI is very evident there, right?
Okay. Dr. Rushi, you shown a slide where you have shown the quantitative results. Okay,
Right.
so there was two things, like one was LinkedIn, another was LinkedIn Ensemble. Could you just throw some light on these 2 points?
Right.
Because
so I believe you're,
the
yes, you're
percentage,
talking
yeah,
about
the percentage, yeah,
ICDAR.
yeah.
So LinkedIn
Your voice is
Microsoft
cracking a little bit.
or OCR, right?
Mhm.
Hi, can
Yeah. Now it's clear.
hello?
Yeah, it's clear
Yeah.
now.
Can you? Okay. Sorry. Yeah, sorry about that. So LinkedIn Ensemble is when we use two classifiers. One was the LinkedIn in-house OCR, and the other was the MS Azure OCR. What Azure OCR will do is it will also give you a score. So then you can put a linear function on top of the two classifier scores and come up with the final score with which you can decide the output, right? So it's a standard linear ensemble.
Okay, so there is a question, and the question is that what percentage of LinkedIn code would you say is a glitch, if else, versus an ML model? Dr. Rushi?
Yeah, I'm trying to pass the question. Could you repeat that again?
Yeah, the question is what percentage of LinkedIn code would you say is a glitch, if else, versus an ML model?
So everything is really an ML model, right? So it's not really anything that is hardwired here. So if you look at this slide, the text detection part, The bounding box detection is a machine learned model. It's a deep learned neural network, right? And the region correction and the skew correction, that's really a projection that you have to learn as well, right? So none of the boxes that I'm showing here, for example, are hardwired or hand coded at all. I mean, each of these boxes is in fact a machine learned model, right? But we have tuned those machine learned models for the specific application at hand, right? So everything is machine learning, if that's the question.
Yeah. Any other questions attendees have any other questions? Okay, there is one question. Has there been any successful implementation of reinforcement learning?
Successful, I'm not super sure. I can come back to you on that, but we are experimenting a lot of RL for search use cases. So what happens is within a search session, you may refine your queries and write better queries or new queries and so on, right? That can serve as a delay feedback signal for what you're looking for. So let's say you search for software job and then software architect job and then software engineering job. And finally, you clicked on something, right? So it also says something about the previous queries and the entire context of the search session. So there is some experimentation going on right now with RL as well. But once we successfully apply, I'm sure we will write um, a blog post or something about it.
Okay, could you give some comments on complexity levels in multimedia ML applications?
So complexity levels in terms of modeling depth or in terms of
development or deployment?
So see, now building a 128 layer deep neural network is not a big deal anymore. I mean, the libraries are available. We have very powerful GPU clusters, thousands of nodes, right? That's not the issue, right? And we have millions and millions of images, so we can do things at scale. So that's not complex anymore. I think the complexity in multimedia still comes from getting good human judgments, right? So going back to the image captioning case, what is to say what is a good training caption that one needs to learn, right? So most of the complexity comes from defining the user human labeling task, the costs assigned with those tasks. And that immediately leads to stuff like active learning and making sure that you sample only the images that will be most informative for the learning task. That's a fairly complex task still, but just building a deep neural network, I think the tooling and the hardware and the data, that's in place at LinkedIn. That's not where the challenge is anymore. So I would say the biggest complexity right now is human judgments, giving humans the most unambiguous instructions so that they can provide meaningful labels back, and ensuring that the humans are actually performing the task to their best abilities.
Okay. Yes, Dr. Rishi, we have some questions, but then it's a time up for us. So what the session was a very beautiful session, which gave insight of how LinkedIn is using image processing, or you can say the different ML algorithms. And means we are the participants as well as I thank you from Aegis. Thanks for the session. Have a great day.
All right. Thank you very much. Bye, everyone.